Hello students, today we will study curl of vector field. So what is curl of vector field? The rotation tendency of vector field about a point, that is nothing but the curl of the vector field. So what is the definition of curl of vector field? So mathematically, curl of vector field is defined as the vector product or cross product of del operator and the vector A is known as the curl of the vector A. Mathematically, it is expressed as curl of vector A is equal to del cross A vector. Okay, we know that del operator, that is vector differential operator, is nothing but del by del xi plus del by del yj plus del by del zk. It is represented in the form of vector, and where a vector can be written in terms of x y z component, that is axi plus ayj plus azk. We will put these values to equation number 1. So equation number 1 implies curl of vector A is nothing but del by del xi plus del by del yj plus del by del zk cross axi plus ayj plus azk. So we know that how to solve the cross product between two vectors. We can use determinant method. So this is determinant method, del cross A. We have to write in first row ijk, in second row the component xyz component of first vector, del by del x, del by del y, del by del z, and then third row we have to write the xyz component of vector ax, ay, and z, ax, ay, az. If we solve this determinant, so this is 3 by 3 determinant, we can solve it easily. So we will get the curl of vector A, that is del cross A vector, is equal to I in the bracket del az by del y minus del ay by del z minus j del az by del x minus del ax by del z plus k del ay by del x minus del a by del x by del y. So this is nothing but the curl of vector A. Now we will see the significance of curl of vector field. Okay, so to understand the physical significance of curl, that is curl of vector field del cross A vector, we have to consider a closed path or closed curve which has this anticlockwise direction. Suppose the area enclosed by this curve or this path is delta S. Okay, and the direction, suppose, and this is, suppose A vector is the vector field, and suppose this is a point on this curved path. Suppose this is any point on this curved path. So the direction of vector field will be the tangent to the curve. So this is the direction of the vector field. Now this is curved path and this is the curve. Suppose this curve is made up of very small elements. So we will consider any one of small elements. Suppose dl, this is blue path is a small element of this curved path, suppose dl. So the tangent to this small element of curve, that is the direction of this small element, that is dl vector. And suppose the suppose theta be the angle, or so let theta be the angle between dl vector and vector field A, and suppose this is the area enclosed by this curve, and this is the direction of unit normal to this surface area. Okay, so now we can put the text here as we understand by the diagram. Consider a small area delta S enclosed by the closed path. Suppose this is closed path and delta S is a small area, and let A be the vector field defined in the region and its direction is tangent to the curve path. So the direction of vector field is the tangent to the curve path, and we have considered a small element dl of the curved path and its direction is represented by the vector dl, that is dl vector, and that is the tangent to the path of this small element. Okay, and theta be the angle between, we have considered the theta be the angle between a vector at any point on the curve and dl. This theta be the angle between dl vector and a vector. Okay, now we will consider the dot product between vector field and this small element vector, that is a vector dot dl vector, and And by the definition of dot product, we know that the a vector dot b vector is ab cos theta. So here a vector dot dl vector is nothing but a dl cos theta. Suppose this is the equation number 1. Now the line integral. Okay, so now the line integral of this vector field for closed path is nothing but this line integral over closed curve or closed path, because curve is closed, or that curved path is closed path. So we can represented that vector field for closed path in the form of line integral. So this is line integral over closed path a dot dl, a vector dot dl. Now a dot dl is, it means that from equation number 1 it is a dl cos theta. So line integral of vector field a for closed path is integral a dl cos theta. Okay, now line integral per unit area. Now line integral of vector field for closed path per unit area will be, that is line integral per unit area, and we know that the area is delta s. So we'll divide this expression, equation number 2, by delta s. So we'll get 1 by delta s, that is close integral line integral over closed path a dot dl is nothing but 1 by delta s line integral over closed path a dl cos theta. So suppose this is the equation number 3. This is the equation number 3. Now n vector unit vector is perpendicular to the area delta s, and positive direction of this n vector represent the direction of line integral. So n cap will be the n cap is the direction of the line integral, and that n cap, that is unit vector, is perpendicular to the area delta s, as we saw in the diagram. This n cap, that is unit vector, is perpendicular to the area delta s. Okay, now suppose this delta s tends to 0, it means the area inside that curve tends to 0. If we limit that area, that is tends to 0, then this equation number 3 is nothing but the curl of vector field a. If we limit this area and this delta s tends to 0, so this will be the curl of vector field a. So this equation number 3 is nothing but curl of vector a into n cap. By n cap, because the direction is in the direction of unit vector, is equal to limit del s tends to 0, that is 1 by del s line integral over a dot vector field a dot dl. So this is nothing but the physical significance of curl of vector a. Okay, curl of vector a into unit vector is nothing but, when area tends to 0, it is nothing but the line integral over vector field per unit area. So line integral over vector field per unit area is nothing but the curl of vector field. Okay, so this is the main equation of physical significance of curl. So in statement we can write these. Thus the curl of vector field a is defined as the vector, the magnitude whose component in the direction of n vector. The curl of vector a is defined as the vector, the magnitude component in the direction of n vector is given by the line integral of vector a for closed path per unit area enclosed by it when area becomes very small. So this is the physical significance of curl of vector a. Now suppose as we say earlier seen that delta s tends to 0, then it will be a curl of vector a. So suppose delta s tends to 0, it means delta s suppose is equal to ds, very small area, that is ds, that is tends to 0. So in place of delta s we can write ds. So this equation will become curl of vector a into n cap is equal to 1 by ds line integral over vector field a dot dl, right? Now we bring this ds on that left hand side, so we'll get this one, curl of vector a into n cap ds is equal to line integral over a dot dl vector. Now we know that unit vector into magnitude of ds is nothing but ds vector, because unit vector is nothing but the vector divided by its magnitude. So unit vector into the magnitude is nothing but the ds vector. So this is nothing but ds vector. In n cap into ds is ds vector. So curl of vector a into ds vector is equal to line integral over closed path a vector dot dl. Now this ds is in here in multiplication, so this ds vector can be shifted to the right hand side, and it will go into the denominator. So curl of vector a is nothing but 1 by ds vector line integral over a dot dl, a vector dot dl. So this is nothing but the equation for the physical significance of curl of vector. So physical significance of curl of vector A is nothing but line integral over vector field dot product, line integral over vector field dot small element vector per unit small area. So this is nothing but the curl of vector a. So this is the overall physical significance of curl of vector a. And if we look at that, on right hand side, a vector is vector, dl vector is vector, and ds vector is vector. So curl of vector a is always a vector. So curl of vector field is always a vector. Suppose curl of any vector is 0, curl of any vector is 0, it means that the rotation tendency of vector field is 0. So rotation tendency is 0 means the vector field is not rotated. So it means that that field is called irrotational field. So what is the another significance of curl? So another significance of curl, if suppose a vector whose curl vanishes, if suppose curl of any vector is 0, then that vector field is nothing but irrotational field. If curl vanishes, then that vector field is not rotated. So that vector field is called irrotational field. Suppose electric field is an example of irrotational field. So curl of electric field is 0, that is del cross E, that is curl of vector E is 0 if electric field is an example of irrotational field. So this is the physical significance of curl. So today we have seen what is curl, its mathematical expression, and what its actually physical significance we have seen mathematically as well as in the form of statement also. So thank you very much.